Okay, and now we'll finish this lecture with a few more examples. So we started with examples, we end with examples, because I think inductive predicates, to really understand them, you have to look at examples. Also here we give the predicates, but sometimes you'll be asked to specify them yourself. So we'll give you a mathematical specification and you'll have to come up with the definition. Or we'll even just say, define a predicate that checks whether a list is sorted. Well, of course, we will not ask just that question because the answer is here, but we'll let you use your imagination to find out what's the best way to capture, an informal context and an informal specification into a formal specification, because this is also one of the things that interactive theory improving is all about. It's not just about apply intro, apply sim, and so on. It's not just about the tactics. It's also about using the whole language that we have to represent things, mathematical, computer science, or real world objects. Okay, so here we have the sorted predicate, which has three cases. We say that the empty list is sorted. Any singleton list is also sorted. And now notice we use curly braces here, and that's good, that's quite convenient. Then we don't have to put as many underscores later when we build proof terms. And then for two or more, then, okay, we have an X, we have a Y, and we have a ZS, which is the rest, right? So this is a list of two or more elements. This is the first element, this is the second element, and this is the rest. Well, here we have two conditions. So we have the condition that X must be smaller or equal Y, and also that the list Y cons ZS, so everything but the X, the rest of the list, is sorted itself, right? And if you have these two conditions, right, so X, Y is sorted and Y, ZS is sorted, then the whole list is sorted, is what we're saying here. Right, so this is how it was defined here. And so, but you see, this is not structural anymore. This is not just nil or cons. We distinguish three cases, which is unusual for lists, but it's just hard to write this particular predicate without doing a three-way distinction. This is just the most natural way to specify it. And then here are some proofs. So we can prove that the empty list is obviously sorted. This is just sorted.nil. Here sorted 2 is just sorted single, and you see we don't need to pass the argument. I mean, we could using at. There we could pass it, but we don't have to. And if we have a longer list, here's a list of length 2, then we have to apply sorted 2 or more, right? The last rule. And that rule has two preconditions, right? That X is less than or equal Y, which is 3 is less than or equal 5, and then that's sorted 5. So we use a lin arith for the first one, and the second rule, the single rule, for the second case. And that's it. And well, this is another way, it's more concise. You can write the whole proof as a proof term, but here you use a tactic for lin arith, so you enter tactic mode here. And here's a longer proof for 7, 9, 9, 11, right? So you have this proof term here that just cascades, all the way to single, one step at a time. So these proof terms are usually developed by just using underscores, right? So you start here, and then, you need two arguments, then you have two holes, and then you're like, here, that's by lin arith. And then you continue here, the parentheses. And then like, how do I prove this? Well, this is sorted 2 or more, two arguments. The first one is by lin arith. You get the idea. So it's not so difficult to develop as it looks like once you have it. The hardest part about this proof is to indent it, properly, because if you don't indent it properly, we're going to subtract points in the homework. Just kidding. So maybe I shouldn't make such jokes. So you can also prove that some lists are not sorted, like the list here. right? So what you do then is, well, first you do an intro because you have this negation, which is really just the same as, right, as an implication. So we do an intro, we do a case distinction, and then what we have is that 17 is less than or equal 13 as an assumption, which is not true. And then, some students sometimes ask, oh, isn't that bad news? And the answer is no, that is excellent news, right? So if you have something contradictory in your assumptions, that means you're done, right? You just need to exhibit the contradiction. If you are in an impossible case, you just need to say, hey, I'm in an impossible case, and then you're rescued, right? If you see something like that in your goal, right, in the target, after the T on its side, then you're in trouble, right? Because you're not going to be able to prove that. So here I just used Linarit. Linarit does this global, analysis of all the arithmetic constraints and in the goal, and in this case was able to solve it. Okay, second examples is palindromes, and palindromes is the same spirit. We also have three cases. We have the nil case. Palindrome is a list that can be read in both directions the same way, like ABBA, the Swedish band, ABBA, right? So that would be a 4-element list, or AHA, which is a Norwegian band that's very much like ABBA, and AHA is also a palindrome, but there are lots of other interesting palindromes in the world, of course, like South Kaupias or something like this. So there's a Finnish one that's quite like a soap seller is a palindrome. So nil is easier to pronounce than the Finnish word, and it's a palindrome as well. Single is a palindrome. And then, for length 2 or more, then you have any word that starts with X, ends with X, and has a palindrome in the middle. And how do I know that XS is a palindrome? Well, because I have a hypothesis here to require it. Well, then that's also a palindrome. And it's very important to have the second case, because if you just have the first and the third case, then you can only have even length palindromes. There's no way to say that a list of length 1 is a palindrome or a list of length 3. And now we already see the danger with inductive predicates. It's very easy to define a predicate called palindrome, and in your head it means palindrome, but it actually doesn't mean palindrome because you forgot one case, or you wrote something completely wrong, you forgot this part here, and so on, right? So for functions, I would say, well, you just have to test them, right? You just write a hash value or eval or hash reduce, and then you check. Unfortunately, for inductive predicates, right now there's no support in Lean for testing them in any way. So there you have to be extra careful, right? So all the homeworks we had 10 out of 10 until now, well, that might, that series of successes might stop if you're not very careful when entering a inductive predicate, because you have to test it yourself, and Lean doesn't help you. So you have to be extremely careful. And this is a big danger in interactive theorem proving, is to specify something, prove some properties about it, and then realize that what you specified isn't what you had in your head. And then, all the theorems that you've proved about it make no sense. And I mean, this is a real trap. I mean, you have papers rejected at conferences for that reason. People make these kind of mistakes, right? So you can prove true properties of, wrong things. So here, just be very careful and prove some lemmas, right? So ultimately, that's the best way. I mean, prove that, a list of length 3 that is a palindrome, like AHA, is actually a palindrome, and so on. So write a few tests. And indeed, here are some tests, right? AA, ABA, right? And here we also see that the palindrome, you see the conclusion here can be an arbitrary term. right? So if you try to do a recursive definition, you would fail here, right? You cannot do pattern matching on something that's not a constructor pattern. Like this plus plus operator is not a constructor, so this fails. So this shows the supremacy of inductive over definitions. You know, when you have when you have a pattern here that doesn't follow the usual, say, structural or constructor-based, you know, pattern matching approach. So so inductive gives us more freedom to have, say, you can even have overlapping, right? So you can have patterns. You can have nil and nil prime, and this doesn't matter. So you have lots of freedom. Each rule is independent, and it doesn't have to stick to any format, except that you have to avoid some really weird things like we saw in illegal 2, right? So you have to stay positive. Let's put it this way. So, okay, so this doesn't work at all. So palindrome is really a good, you know, example of a predicate that should be declared inductively. And yeah, we have a couple of proofs here, which are in the same style as those that we've done above. And then we have our first nice result, which is that the reverse of a palindrome is a palindrome. All right, so here we have the hypothesis that XS is a palindrome, and now we prove that its reverse is a palindrome. And what we see is that XS is applied to reverse, right, which we define, let's see, that's our own reverse, that's very good, we defined earlier, okay? So we have this hypothesis here that will help us, because the idea is that we're going to exploit the fact that we know how, or we can know by induction how we prove XS to be a palindrome, and we're going to use this information to prove that its reverse is a palindrome. And so we do an induction, a rule induction on this hypothesis. And then, of course, we have 3 goals, you know, the nil case, the single case, the sandwich case. And the nil case, we just have to prove that the reverse of nil is a palindrome, all right? And well, reverse of nil by computation is the same as nil, so we can just apply the rule and it will apply up to computation. So we don't even need to simplify or anything. You can if you want, but these steps are not necessary. For single, well, the reverse of singleton will be a singleton, so we can do the exact same thing. I wrote it with exact, I could have written it with apply as well, I think. Yeah, there you go. And just for documentation. And then in the last case, I see reverse of, you know, something complicated with, you know, append and singleton list. So we're just going to simplify the definition of reverse and use, I mean, I could do it in 2 steps maybe to see a bit better what happens here. So this does something, but not much. And then we have reverse applied to append. So we also want to do reverse append, right? Which was a lemma we proved here. Okay, so I'll put them back together because that looks more tidy. And then we're in a good shape because we have an x at the front, and then a const, a reverse, and then plus plus x. It's almost the format we want, right? It's, you know, what we want is a singleton here plus plus, but you know, a singleton plus plus is the same as const with a single element, and that's by computation. So I don't even need to rewrite or do intermediate steps with a have or anything. I can just apply directly the third introduction rule, exploiting the induction hypothesis here, because we need, you see, we need the induction hypothesis when applying, you know, the sandwich rule. It requires, of course, the body here to be a palindrome, which is exactly what the induction hypothesis gives us. Of course, here this fits very well because we're starting with a palindrome and we're proving a palindrome, and the list has the same length, and actually the list is the same. So, you know, we map the proof quite directly, a nil to a nil, single to single, a sandwich to a sandwich. Sandwich. There are 2 more examples in the file. So there's a full binary tree, which is, the idea is that we have this binary tree type that we saw in lecture 4, I think. Yeah. And now we define a predicate on it to identify those binary trees that have that are full. So you know where each layer has, you know, is fully populated by nodes, and then the very last layer has empty leaves, right? So here's my whiteboard. So this is not a full tree. Whereas this is, you see, because you have a like a nice layer at the bottom that's all at the same level. So I'm leaving this one as an exercise for you to study. There's documentation as usual in our favorite guide, or not so favorite guide, I don't know, depends on the reader. And also here you have a notion of first order terms. So first order terms are, well, they're the terms that you're probably more familiar with. So when you write x or f of x or f of a, b, or, well, for example, sine, so sine of 5, these are all first order terms, right? So they have parentheses, they have commas, so unlike lean terms, which are based on functional programming. And here you see we have a type where we have, you know, a term is either a variable, like x here, or it's a function symbol, which is applied to a list of arguments. So for example, here it's a list of length 2. And we have alpha and beta. So beta is the alphabet used for variables, and alpha is the alphabet used for function symbols. So you could use strings for both, but you could also say, oh, I want my variables to be integers or de Bruijn indices, and you might say, oh, I want my functions to be strings, right? So that's first order terms. And again, I mean, we have a few, you have the notion of well-formed. So for example, you can say that sine should take one argument. And then if you write something like this, you would say, this is not well-formed. If you write that, you say, this is not well-formed. You have to have exactly the right number of arguments. And you have to do it recursively, right? So this is fine, but this is not fine. So this is what the well-formed predicate does. And variable free just checks recursively that there are no variables in the term, that you have a term that consists only, for example, this term here has no variables. Whereas this one here, where x is a variable, definitely has a variable. Okay, so that concludes our review of inductive predicates and logic programming in Lean.